So in class on Friday, we started but did not finish this one curve sketching example. So I'll go through the last two steps now. Just to recall, we were sketching the graph of this function, this rational function. We found its domain, the xy intercepts, the asymptotes, meaning vertical, horizontal, and also slant asymptotes, now that we've learned about those. We looked at the derivative, the first derivative, to find the intervals of increase and decrease, and then also the local max and min. And I think it was right after class, some students asked about how you could have places where you get, like here we see that we have f is increasing and then decreasing, and so we can say, oh, there's a local max here. Now, we do also have to make sure that if it's increasing and decreasing, we do have a situation where there is a local max because that x value here being -3 is in the domain. Because it is possible that you could have increasing then decreasing, but there was a vertical asymptote. But you can kind of catch that too if once you plug in that x value to find the y value, if you don't get anything, it's like, oh no, that was a discontinuity, that kind of thing. Okay, so as promised, I'll finish up the example now. So, step 6 is to look at concavity. I'll give us more space here. I'll write out that the second derivative again. So that was 6x times x squared plus 9 over x squared minus 3 all cubed. And now we want to do some sign analysis on this. And to do that, we'll start off by looking for the roots of the numerator and denominator. And just to remind you of why we do that, that's because we want to see where different pieces of that function might change sign. So for instance, from the numerator we get x is equal to 0 as a root, because when x is 0, the top is going to be 0. But specifically, if you think about it, for x values on either side of 0, this part that's the 6x is going to change from negative to positive, and that's going to change everything from negative to positive, right? We have no roots coming from this. You can check for yourself, either by looking at the discriminant using the quadratic formula, or you can look at the graph, or you can just try to solve x squared is equal to -9. You'll get stuck. So no roots from there. But then from the denominator, we get plus and minus √3. And that's it. So this is what we'll put in our table. So we've got the intervals, -∞, -√3, -√3 to 0, 0 to √3, √3 to infinity. Then we get our factors. We've got 6x. X squared plus 9 is always going to be positive, but as I mentioned in class the other day, I always like to just include all of the factors so that I never end up accidentally missing them, when it really counts. Okay, so 6x we know will be negative before 0, positive after. X squared plus 9 is always positive. And then x squared minus 3 cubed. Now this one we can factor as x minus √3 times x plus √3, and both of them cubed. But I'm just being a little lazy in combining them. And using that, I know that it's just that normal graph of x squared shifted down by 3. And so you can kind of see from here where will be positive or negative. Okay, so you will be positive outside of -√3, then dip below the x-axis, and we'll be positive again. So together then we go negative, positive, negative, positive. And so F is concave down, concave up, concave down, concave up. And now we can put all of this together into a graph. We've got odd symmetry here. So I can kind of use that a little bit to guide us, but let's see. Okay, so we had, I'm just looking at, we had again, so we've got that vertical asymptote at negative root 3. I'm going to just put that like here. Another one at positive root 3. It's about the same. And let's see, what else can we use here? We saw no horizontal asymptotes, but we did have a slant asymptote of y is equal to x. And so what we can do now is add that. And so we know then that the long-term behavior of our function is going to be such that it kind of follows that. Okay, I did say something in the steps about kind of combining all this information into a big table, which is kind of tedious, but what we can do actually, because the table for f prime from this step has a lot of the same numbers as the one for the second derivative. I'm just going to kind of, okay, I'm just going to like add our concavity information to that one. So here, if we add in what was happening for concavity, we can see that F is concave down, down, again until negative root 3. Then it's concave up until 0, then concave down until root 3, and then concave up afterwards. Cool. We had that local max at negative, x is negative 3, y is negative 9 over 2, and the local min at x is equal to 3, and y is 9 over 4. So let's place those now too. So let's say this is about 3, or actually more like that. I'm not really doing this very exact, but it'll work out okay. Then let's put our local min here. So those 3 and 9 over 2. Then we had another one that was at negative 3. Oops, I wrote 3. Great. Okay, so then now we can just put together the information from the table and start the sketch, really. So we see that our function starts off as we head towards the local min, or the local max at negative 3. We are increasing and concave down. And we know that we've also got that slant asymptote, so we can start kind of closer to that slant asymptote, and then we're increasing while being concave down. I'm going to get a little bit more curved. Okay. Then we see that once we're at negative 3, we start decreasing while still being concave down towards that vertical asymptote at negative root 3. Then we are now on the other side of that vertical asymptote at negative root 3. And if we actually scroll up, we can use these limits. So at negative root 3, we see that we're negative infinity on the left-hand side, positive infinity on the right-hand side. It ends up being the same for the one at root 3 too. So we have negative infinity on the left-hand side, and then it's positive infinity on the right-hand side. Actually, we can kind of do ourselves a solid and put those arrows in there already for root 3. Okay, so then from negative root 3 to 0, we should be concave up now while decreasing. Drew this a little too curved. And we know that we'll go through that intercept at 0. So we'll draw that in as well. Okay, so concave up. Go through here, concave down to our vertical asymptote. Awesome. Yeah, that was what we did from 0 to root 3. That's good. And then now we are, oh, I guess I didn't point out that, shoot. 0, 0 is an inflection point. Sorry. There we go. Okay, because that's where we have a change in concavity that's actually a point. We do have changes of concavity at plus or minus root 3, but there's no point there. It's a vertical asymptote. Okay, and then for root 3 to 3, we're decreasing concave up, and we know we have to go towards that local min. So we're decreasing concave up, and then until from 3 to infinity, we're now increasing and concave up still. So kind of following that slant asymptote. And then that's it. That's our graph. Yeah, I'll upload this link. Put it just on this page here. Thanks for watching and hopefully following through the rest of this example. I think we'll do number 4 actually on the Monday when we get back, just because there's some cool stuff going on with that function. So